Now here we are at test ID 1 and the subject is communications, and the question is question number 46. Now this question is related to B, or what we call as the bit error rate of a digital communication problem. So here the modulation scheme, that is that is used to transmit the data is BPSK, a binary phase shift keying. So +1 is transmitted by a sinusoid whose value is AC cos omega CT, and a -1 or a bit 1 is transmitted by this, and a bit 0 is transmitted by a data minus AC cos omega CT. Now it is given in this question that it is required to transmit 1.5 into 10 power 6 bits per second with the probability of error, that is a bit error probability, should be less than 10 power minus 6. Now we very well know that if this is the bandwidth, that is since it's a binary modulation scheme, this is our bandwidth itself, that is the sample rate at which the data is coming is equal to the bandwidth itself. Hence the bandwidth, if you look at the spectrum of this signal, assuming it's given in the question that it's assumed to be a raised cosine pulse shapes, then one can expect that the spectrum, since it is directly multiplied by cosine omega CT, it would be shifted to omega C and minus omega C. Now it is also given that the channel noise, which is a white noise in this case, to be 10 power minus 8. This is the noise spectral density whose units is watts per hertz. Now the question that what the question asks is, what is the minimum signal power that is required at the receiver such that the probability of error, that is, let's call it TE or bit error, is less than 10 power minus 6. Now we know that for a BPSK modulation scheme, the probability of error is given by Q of root of 2 EB by N0, where EB is the bit energy and N0 is the noise spectral density whose units, as described above, was watts per hertz. Now it is also known that Sn of omega is equal to N0 by 2, which is equal to, in this problem, is 10 power minus 8 watt per hertz. Now our question in this place, now we will just substitute these values. Now Q function is nothing but, it's already assumed we know what a Q function is. Q of x is nothing but the tail probability distribution, tail probability of a Gaussian function. Let's say we have a Gaussian PDF, a Gaussian probability density function. Then Q of x is simply the area under the integral of the tail curve of a Gaussian PDF, where Q of x is given by integral x to infinity e power minus x squared by 2 sigma square dx, or by 2, it's normalized to unity, 1 by root 2 pi. This is the expression for Q of x. Now substituting this value, the values of Q for two values have already been given. Q of 4.76 is given to be 10 power minus 6 in the question itself, and Q of 5.21 is given to be 10 power minus 8. Now what we have here in this problem is Q of 2 EB by N0. Since this is the probability of bit error rate and we want this to be less than or equal to, so we will compute the minimum bit energy necessary. So we will take a equality 10 power minus 6. Now when this is equal to 10 power minus 6, what we have is, substituting in the result given in this question, we simply have E bit by N0 is equal to 4.76. Square root of this is equal to this. Now after some manipulations, squaring it and then dividing it by 2, we get EB by N0 approximately 11.7. From this we can compute the bit energy, that is the bit energy which is necessary to transmit a single pulse. which is equal to 11.7 into n naught, and we found our n naught to be 2 into 10 power minus 8 from this expression. So if we know what is the bit energy now, from the bit energy, the question is signal power. What is the necessary signal power? Now it is very well known that since we know the bit energy, then we'll have to simply multiply it by power is nothing but rate of doing work. We can even come from a definition from that angle also. Then it would simply boil down to EB times RB, where RB is the rate at which the bits are arriving, or the bit rate of the modulation scheme. So this is EB into RB. Hence you have 11.7 into n naught into 1.5 into 10 power 6 watts power. Hence it is in watts. Now, doing these computations, one would readily get an answer to be 0.34 watts, and hence the correct choice is A.